Hi Pre-Calc students, it's time for a couple fairly challenging lessons on line 3.6 and 3.7. So I'm going to go fairly rapidly here, but feel free to pause often to write down some graphs and ponder what's going on here. So critical points and extrema is lesson 3.6. Critical points, as you can see, are points in a graph in which a line drawn tangent to the curve is horizontal or vertical. You may remember from your geometry days that tangent, it is a trig function that we'll talk about, but it's also a line that just kind of grazes the edge of a graph. So on this first one here, I'm drawing a tangent. You can see that's going to be a horizontal line, kind of way at the top of that parabola. Here the tangent line would be on the bottom here, just grazing that graph at one point on the bottom. Here it's a little bit trickier. There is something called a vertical tangent right here on this thing called the point of inflection. So the maximum, of course, would be here. That's where that tangent line is. The minimum of the graph would be here where that tangent line is. This point of inflection right here, a little bit tricky to see. It's also, in calculus we talk about this. Notice the curvature of the line. We say this graph is curved up or concaved up, but down here is where it's concave, this is where it's concave down, curvature is down. Here it's concaved up. You can see that point where it changes is called that point of inflection. We also have different types of maximums and minimums, and these are classified as extrema. Clearly this point down here is a bottom point, it's a low point, it's going to be a minimum, but because it's the very minimum of this graph, we call this the absolute minimum. Not just any old minimum. Now contrast that with this point right here. Clearly that's a minimum point on the graph, but it's not the very lowest point, so we call this a relative minimum. So with these extrema, they can be absolute or relative. Let's look at one more that we have here on this graph, which is this one. You can probably guess what this is going to be. It's kind of a high point, it's a maximum point, but it's obviously not the highest point on the graph. So we call this a relative maximum. A lot of times we'll just abbreviate maximum and minimums as maxes and mins. So those are types of extrema that we have on it. Now let's actually look at some examples here. Here is a function that you can put in your calculator, x cubed minus 8x plus 3. And you might have to change your scale when you graph these buggers, and it just will need some experimentation on your part. Here's the scale that I use for this particular graph, which gives me a nice window that I can clearly see the graph pretty nicely. Now clearly we're going to have maximums and minimums here. The way to really establish what those are, and oftentimes we want you to designate them by ordered pairs, is to get to that calculate menu on your calculator, that second and trace. And I just showed you how to get to this maximum one here. When you get there, you can scroll around. It'll ask you for a left bound and a right bound and a guess. Eventually then you'll be able to get the exact ordered pair here where that maximum occurs. So if we rounded it a bit, we might say that the maximum is the point negative 1.63, 11.71. We could do the same thing minimum wise as well. Now the one thing our calculator doesn't do is give us that point of inflection. There would indeed be one in this case, as you can see where that curvature changes from opening downward to opening upward. There's going to be one of those points of inflection here. We'll learn in calculus, those of you that are fortunate to take that class, you'll learn how to really nail down what that point is there too. Alright, here's another function. Can we just classify what these extrema are? 3x to the fourth minus 4x cubed. I've gone ahead and graphed that. It tells us that the critical points are going to be at 0 and 1, so we just want to classify what those are. Well, clearly at 0, this is not going to be a maximum or minimum point here. So that point right there has to be that point of inflection. And you can also see that the curvature of the graph changes there as well. So that's another key way to think about that point of inflection. The graph is kind of opening upward here. Here it's opening downward a bit, so that point of inflection is going to be where that changes. Alright, and then clearly we have another point here. What would I classify that as? That's at x equals 1. Certainly it's a minimum. Is it the absolute minimum? And yeah, I think we'd have to say yes, that it is that absolute minimum. The graph doesn't appear to go any lower than that y value wise. Alright, so now we're going on to lesson 3.7. As you can see, lots of heavy-duty graphing here in these lessons, to be sure. When you hear that word rational in math, by now you've heard this quite a bit, you should always think everyone's favorite, fractions. So a rational function will kind of be, I'm going to call it fraction-y. So it will look like a fraction. There'll be lots of variables in there in most cases, but it basically will look like a fraction. And the way to really analyze these many times is with something called asymptotes. This is a word you've probably heard before. It's a line that a graph approaches but usually doesn't intersect. Occasionally it will intersect it or cross it briefly, but the graph usually just travels on a path really close to these asymptotes. 3 different kinds, as you can see: vertical, horizontal, and slant. We're going to look at kinds now. Here's the vertical kind, and of course the vertical kind is easy to pick up because it's when the graph shoots way up or shoots way down. The official definition you can read right there, saying that, again, when you see f of x, that's the y values. So the y values are either going to approach infinity, that means get very big, or approach negative infinity, that means get very small, as your x values approach them. So as your x values get very close, your y values will go really high or really low. Now, as you can see in this particular graph here, that the vertical asymptote is x equals 1. And a lot of you have maybe figured out that you can really focus on the denominator. It's that denominator which really determines what that vertical asymptote is going to be. Remember, we never want the denominator to equal 0. So in this case, if indeed x was 1, that denominator would be 0. So pretty much anything that makes that denominator be 0 can be considered that vertical asymptote. Notice also that vertical asymptotes are always in the form x equals something, hence the vertical. Now, horizontal asymptotes a bit trickier, perhaps, but again, you can largely see those pretty well. Here's that same function we used before. Horizontal asymptotes are where the graph tends to flatten out and go right along a horizontal line. And notice the form always has to be y equals something, y equals b. In this case, notice that we're looking at really big x values or really small x values. As x approaches infinity or as x approaches negative infinity, what are the y values doing? So notice that this is extremely similar to that end behavior that we talked about last lesson. End behavior and horizontal asymptotes are very closely linked. In addition to just looking at the graph, you can also use your calculator for help here, and that's just to look at some really big x values. So I went to the table setup, that second in window I believe on your calculator, and just put my starting value quite large there at 1,000, and even had my table go up by that much. Then if you look at your table, second in graph, you can see what those y values are going to be. Even as my x values get really big, you can see my y values are all going to be really close to 1. They'll never get to 1, but they're going to be really close to that. So that's why we would say that in this particular case anyway, that the horizontal asymptote would be y equals 1. Now there's also asymptote. This one's a little trickier. It's called the slant asymptote. So not horizontal, not vertical, but a slanty line or an oblique line would be the mathematical term. And once again, you'll be able to recognize this on the graph as we'll see in our next example. Now note though that this can only occur when the degree, and by degree we mean the power of the function, sorry about that, I meant to use this thing, the power of the numerator of a rational function is exactly 1 greater than the degree of the denominator. That's the only time you might have this slant asymptote. Example of this, here's a goofy looking rational function. Clearly by the degree here we mean 2, or the second power. That's the biggest power here. This one has a biggest power of 1, so a slant asymptote might occur in one like this. And sure enough, if we graph this thing, we see that, yeah, it does look like there's going to be a slanty line here that the graph never gets to, but certainly follows very closely. Notice also there is a vertical asymptote here too, isn't it? And the denominator tells you what that is going to be pretty much. Okay? I wonder if I graphed that incorrectly. Maybe I should have had an x plus 4 there, but whatever. Let's see if we can figure out what that slant asymptote is. And to do this, we're going to do everybody's favorite thing, and that is called long division. So you might remember doing this with numbers back in elementary, but let's just try it here with rational numbers and things like that. So what I'm going to do is write my expression here. I'm going to divide it by x plus 4 here. I think I meant to have that be an x plus 4 is what that should be in there. Now this is going to be kind of goofy, so hang in there with us. When we long divide, we want to try to knock out this first value all the time. We want to try to knock this out. So I asked myself, what would I multiply x by to get 4x squared? And sure enough, it would be 4x. And then I multiply. This is what you did when you did it with numbers anyway. Multiply 4x times x to get 4x squared, and 4x times 4 to get 16x. And then you might recall when you did long division, you actually did some subtracting. I think it's beneficial to change signs and add. So I'm going to change those two signs there. And now I'm going to add these up. So clearly those 4x squareds will cancel out. 6x minus 16x is negative 10x, like that. I bring down my negative 37 like that. And now I repeat that process again. So what would I have to multiply x by to get negative 10x? I always want to knock this guy out. And sure enough, it's going to be minus 10. So I go ahead and multiply that out again. Negative 10x minus 40. And I'm going to change my sign once again. Remember, subtracting is the same as adding the opposite. So now when I do that, I see that my 10x's cancel out. I get a remainder here of 3. Doesn't really matter too much. My final answer then is actually going to be this slant asymptote is y equals my quotient up here, which is 4x minus 10. You could check that out on the calculator and see that sure enough, if you graph that, it would indeed be this line that slices right through here as the slant asymptote. So lots of stuff to comprehend here in these couple lessons. We'll practice on it in class, so we'll see you guys then.